So we're still waiting for some people to come back, so you can just start hacking away on the example from last time. An important point is when you type in the salloc command with these flags over here, that gives you one node for half an hour, for 30 minutes. So if later on it tells you something like, you don't have an allocation or you don't have a node, I forget exactly what the error message is, that's just saying that it's time to grab another node. If you want to grab a node for a bit longer, you can go -T 60, and that'll get 60 minutes. Okay, so I think we have everybody back in here now. So I just told everybody before, if you just came back in, that when you type in the salloc command to get your node to run on, that will give you the node for 30 minutes. So after the 30 minutes is up, it'll say something like, your allocation has been relinquished or has expired. So if you try to run something and it gives you an error message like, you don't have the resources to run this, you just need to type salloc again to get the node back. And if we're about to do a particularly long set of exercises and you want to make sure that you keep the node for longer than 30 minutes, you can pass in a flag -T 60, and -T 60 will give you the allocation, will give you 60 minutes. That's a minus. Okay, so did anybody figure out what this code is doing? Can we have someone who doesn't work for CSCS please volunteer an explanation? Yeah. Okay, so I will walk us through it. So we do this part here. We are just loading. We get a number from the command line, and then we go 1 shifted to the left to that number. This is a little trick. It's a little bit shifting trick. If you take the number 1 and you shift it bitwise to the left, pow times, the number you get as a result will be 2 to the power of pow. So that's just a little trick. We get a CUDA handle. Let's not worry too much about that. Then we allocate some memory, and we use this function called malloc managed, and we're allocating n here, and we've got this double template parameter and some numbers here. But you might have noted this isn't the CUDA managed malloc that we saw, or CUDA managed malloc that I showed you in the slides. This is something else. And if you went to the util.hpp, you would see we have this template function here. Now, when we're using these low-level C APIs for allocating memory and things like this, and for copying memory, I always make lots of mistakes because when you allocate space for n doubles, you always need to allocate space for, you actually have to supply how much memory you want to allocate in bytes. So you've got to say n times size of double. And I always end up making the mistake of just asking for n bytes and having segmentation faults and chasing my own tail. So this is just a little wrapper. So it takes in a size argument, it's templated on a type, and it takes a default value. So we do the CUDA malloc managed, we get the status here, and then we check the error, and we'll have a look at this later on, exactly what this does. And then we initialize the memory that we've just allocated to the value. So we don't have to provide a value here. We can just ask for n. This is saying make the default value equal to whatever the default value is for that type. So for most types, basic number types like integers and floats and doubles in C++, the default type is 0. So if we don't ask for anything, it's just going to allocate the memory to 0. We allocate the memory, we check that there weren't any errors, then standard fill is part of the C++ STL, and that's basically saying from P to P plus N, for the length of this memory we've just allocated, fill it with this value. So we're just initializing the memory. So malloc managed, that's a little helper function. And we're going to be writing a few of these and using these throughout the course, because using this saves you a lot of typing. So when we're doing the examples later on, you don't want to do all of this error checking and size of t stuff. So we've allocated space for two vectors, x and y. We call something called CUDA Profiler start, and we'll see what that means in a moment. We start, this looks to me like we're starting a timer. And then the next interesting bit is we call a function called cuBLAS DAXB. I've got no idea how to actually pronounce that. Did anybody look up what cuBLAS DAXB does? Because the nice thing about CUDA is that it has got very good online documentation. So let's see how good that is. cuBLAS DAXB. So I think they're down here. So BLAS, as I said earlier, this was this basic linear algebra subroutine library. And it has, if you want, it's got things for everything from as simple as adding two vectors together to doing matrix-matrix multiplications and solving triangular linear systems. And Nvidia have gone and implemented all of these to run on the GPU and provided an interface for them. So here I can look at the cuBLAS DAXB. There's also a cuBLAS SAXB, a CAXB, I suppose, and one with the Z. The difference between these is this is for single precision, so for floating point values. This is for double precision, so 64-bit floating point values. These are 32-bit ones. The one with the C is for complex, and Z is for double complex values. And if you look at this down here, what we're doing is it basically, and you pass in some pointers to some X and some Y, and alpha, which is going to be a constant value, and some extra information. And at the end of the day, what this does is this adds the two vectors together. So Y, the output value in Y is going to be A times the input value in X plus the original value in Y. But basically, it's for adding two vectors together with a little linear combination. Well, and where's my terminal? Okay, so we're adding two vectors together, and then we started a time. We got the time at the start, and now we're going to get the time at the end and take off the time at the start and print out the time that was taken. And then we've got a little loop here that goes and checks that we actually got the correct answer. So I think we were expecting that the answer of adding these two vectors together would be 6. Okay, and we count the number of errors, and then we print a little message at the bottom saying how long it took, and how long it took, and how many errors were found. Now, what did you notice when you ran it? Lots of errors. Yep. And that's actually to be expected. Did anybody try to run it with different size arrays and see how long it took? Because when we look at that, we actually start to get a clue for what went wrong. So I'm just going to type make, and then I'm actually going to load the module here. Module load, CUDA toolkit, and GCC. Okay, And now I'm going to get myself a reservation. Okay, and now we are ready to go. Let's go. srun managed, and let's run it with 16, for example. So that's going to run it with, so when I use 16, the arrays are going to be of size 2 to the 16. So we're getting an array with 2 to the 16 values in it and adding it to another array with 2 to the 16 values in it. 2 to the 16 is about 65,000. Okay, and you can see I've got exactly 65,536 errors. And we can see that it took less than a millisecond to run. Now, let's try to run it for something a bit bigger, shall we? Okay, so if I was to make this twice as big, so I just have to type in 21 here, because remember, every time I make the input value bigger, I'm making the problem twice as big. How long would you expect it to take to run? If it took, 0.4 milliseconds to run. If it took 0.4 milliseconds to run with a million entries, now I'm going to run it with 2 million entries. How long would you expect it to take? Sorry? I heard someone say the same, but how much would you expect it to take in a sane and sensible universe? You would expect it to take twice as long, because it's doing twice as much work. But we see that it takes about the same amount of time. Okay. Now the next, we're going to find out what's going on there in a moment. The next thing I would like to do is run the CUDA profiler, because I believe that was the next item I had on the list. Ugh. Come on, hop onto the other desktop, please. So the answer to does it work is no. It doesn't seem to be working right now because our little error check is giving us errors. So I don't have any formal slides about NVProf. That's the profiler that comes with the Nvidia toolkit. I thought we would just learn a little bit about NVProf by continuously using it throughout these exercises. So to run NVProf is pretty simple to use, and you can run it. The most basic way to run it is you just type in NVProf, the name of your program that you want to run, and then the normal flags that you would pass to your program. So let's do that. But because we want to do this on the GPU, we have to use srun. So let's do it. srun NVProf managed. Okay, so this is running NVProf without any special flags for NVProf. And if we go back up to here, NVProf it will print out a little banner saying, I am profiling this process. And then it will give you some output. And the first bit of output it shows us is the CUDA kernels that we've launched. So the CUDA kernels are the work you've actually launched on the GPU. So it's ignoring all of the other stuff you're doing in your application and just talking about the work that you launched on the GPU. And there's actually only one bit of serious work that we launch on the GPU, and that's this bit where we add these two vectors together. So we called this cublast daxp function, but underneath the hood, this cublast daxp function is calling a CUDA kernel called axp kernel val. And we're going to learn about what CUDA kernels are and stuff. That's part of the next subject. But we can see here that we called it once, which makes sense, and it took this amount of time, and it took 99.72% of the application's time. We've also got some unified memory profiling results here. Or it also tells us that we copied some memory from host to device, a tiny bit of memory. But then we've got some extra information here about the unified memory. And we made 22 transfers from host to device, total of 512 kilobytes. Now 512 kilobytes, I ran it with 15. We had to copy over 2 arrays, so I'm pretty sure if my mental arithmetic's right, that's basically this times 2 times 8 is going to be 512 kilobytes. I'm sure someone's checking that right now, of data. So that you can see that the unified memory, because remember what we did is we did a malloc. We allocated some memory using managed malloc, and then we initialized all those values to be equal to some values on the CPU. Then when we ran our kernel, we passed this memory into the kernel saying, execute with this memory. So when it started using that memory, it had to start copying the memory over. And here we can see some statistics about that. And then down here it shows us some information about API calls. So we called CUDA free and we called CUDA malloc managed. There's a whole bunch of other calls here that we didn't explicitly make. We didn't ever call CUDA memcopy or CUDA launch. These were launched in the background by the CUDA runtime. But we can see here that we called, it took a long time to, some of these calls took quite a long time. It took, almost a second, or over half a second to call CUDA free. And the reason for this will become clear in a bit. But this is quite nice if you really know what you're looking at and you know what your application looks like. But we can also use a graphic. They've got a nice graphical user interface. There's many more options that we can use. So let's have a look at these. Yes. Here's something I prepared earlier. So now we are calling NVProf, and we're calling it, and here's our executable with the argument, and then here is some extra flags, but because these flags come before the function, the program that we're profiling, these flags are going to get passed into NVProf. And so now we're giving NVProf a bit more information about what we would like it to profile and what we would like it to test. And we're telling it, don't print stuff to the screen, save the profile results to a file. And this is the name of the file we want you to save it to. And don't profile from the start. So you might see inside the code, I had a CUDA profiler start and a CUDA profiler stop function calls inside the code. So what you can do, because often if you've got a really big application, you don't want to profile and get a profile information for the whole thing. Usually you're just focusing on optimizing a small part of the application and you don't want all this extra information. That's just noise. So you can actually, inside your code, instrument your code and say, start the CUDA profiler here, stop the CUDA profiler here, so that your output is just the bit that you're interested in. And to do that, you have to add those calls into your code, and then when you run NVProf, you have to say, don't start profiling at the start, wait until I tell you to start and stop. And -f, that just means that if this file here already exists, just overwrite it. Don't throw an error. So let's run this. Application received a signal 11. Crikey. Okay, so we had a signal 11, which means a segmentation fault, which is not good, but we still managed to get the profile out. I suspect the segmentation fault might be because the program that we're currently profiling has got some pretty bad errors in it. And if you want to follow along and maybe do this yourself, you have to, when you log on using SSH, you have to SSH minus capital X or minus capital Y to turn on the X window forwarding. because when I run NVVP now, it's a graphical, it has a graphical interface. So to use that from a remote terminal, you've got to use the -X or -Y flag. I believe I don't have the slide available, but I believe I had that in the original slide thing. .nvvp. Oh. Okay. So I debugged this on my Linux desktop system. Sam, how do I fix up this locale?
Language equals, locale equals C, lang equals C.
Sorry?
Lang, actually.
Lang equals C, like that?
No.
Using fallback C locale.
That's not the fundamental problem.
Oh, do I not have X Windows installed?
Well, it's not running.
Okay, I'm going to have you got it up and running? That'd be, yeah. And I will quickly, so just bear with me for a moment. I will try to, thanks. I'll see if I can do this with a minimum of pain. Sorry, this is a new laptop, and I keep on discovering things that I haven't installed on it. So, by the way, if you've got the same error as me, you need to install X Windows on your Mac. Okay, this is going to work. Okay, so I might let that install, and we'll come back to that in a moment. Did anybody actually manage to run the profiler and get? So what we would hope to see is, oh gosh, that is taking a long time to install. What we would hope to see is, if you look carefully, you'll see where the kernel was running, and then CPU. No, I'll come back to it later. We're going to look at the CUDA profiler output for another, in the next little example in a moment as well. So then it might be good actually to put the two profiler outputs side by side and have a close look at them. So, thanks, Tibor. Oh, I need to log out and log back in. Okay, I'll do that in a bit. So we saw that it didn't quite work. Logically, it looked like it would allocate the memory, run the kernel, and then we can check our answer and we can take the time. What happened? What went on? And to do this, to understand what went on, we had to know a little bit about how work is launched on the GPU and the CPU. So here's a little bit of application code where we basically call some kernel on the GPU. So in the example we had before, we had this cuBLAS DAXB, which was just a normal looking C function. But underneath, that was launching some work on the GPU. And we're going to learn, don't worry, we're going to learn what all that looks like. And then it makes a CPU call. What does that actually look like? Well, what does that actually do? Here's what the execution looks like. This is the column showing what's running on the GPU. So this is time, basically starting at time equals 0 and running down. So when we do this here, when we make GPU call, we call a thin little function. A thin little function is called that basically packs up the parameters for this thing we're going to run on the GPU, copies them from the host to the device, and then calls the GPU, calls some low-level API to say, OK, now you can run the kernel. And then when it's finished with that, at some point soon after then, the kernel will start running on the GPU. And it's going to start running for a certain amount of time. But the host, the CPU and the GPU are running asynchronously. So that as soon as this kernel has been started, the CPU just keeps on starts doing the next bit of work. I.e., when you make this call, it doesn't wait for this work on the GPU to finish before you start doing the next thing. They run asynchronously. And this is a nice sort of default behavior because it means that it's very easy to overlap work on the CPU and the GPU. If you've got some work that you want to do on the GPU and some work that you can do on the CPU at the same time, you can overlap them very easily. But it's a classic CUDA beginner's mistake. I remember I spent a day when I first tried to teach myself to program CUDA because I was making the assumption that these things were all synchronous, and they weren't. So yeah, the CPU just launches the GPU code and then just straight away starts launching it, doing its own work. The GPU runs the code asynchronously, and there's no synchronization between the two after that. So the problem in this case is that the CPU call and GPU call are both accessing, or you can have a problem if they both access the same memory at the same time. Because managed memory is quite nice in that the CPU can access it and the GPU can access it, but if both try to access it at the same time, the memory page can't be in two locations at the same time and you're going to get some strange behavior. And also, another classic mistake that you often make is you might want to time how long a GPU call takes. So you put a little call up here to say start timer, then you call GPU call and you say stop timer. But all you actually end up recording is how long it took to launch the kernel. You didn't record how long it took to execute the kernel. So that's why when I increased the amount of work to do on the GPU, the amount of time it took didn't double. When we doubled the amount of work, it didn't actually double the time to solution. So the solution, what we actually have to do is we have to somehow synchronize calls between the code that runs on the GPU and code that runs on the CPU. They've got to be synchronized somehow when we know that we could have these potential conflicts where they both want to access the same memory. And this is a pretty big topic, and I'm going to be going into this in a later set of slides tomorrow or the day after tomorrow. So we want to actually put some sort of synchronization in that says, don't do this work here until this work here has finished, if this work here depends on that having finished. Now, it can be, as you can see, it can be pretty difficult. Sorry, did you have a question?
Yes, one basic question regarding, we use this function to allocate memory now, right? And we have a managed system, the CPU, GPU memories.
Yes.
Where would it have put it now? Like it's on the GPU memory now, this array?
Okay, so the question is when I use this managed malloc to allocate memory, where is that memory? And by default, it's on the CPU, it's in the host memory space, but I've not seen it, and by default means the behavior that I have observed. But I haven't seen in the documentation that any guarantee that says the memory will be X. And you might actually be able to configure that as to where the memory should start out. But you have to be careful. So when you have this is a very simple little application, and it was pretty easy for us to write this code and then make a mistake. you can imagine that for a larger application, very quickly you can end up in some situations where you get some strange behavior. And the program didn't crash, it didn't fall over, it just gave us the wrong answer. So you've got to be careful. And one way, if you're getting strange behavior, or if you're getting strange crashes, so strange behavior might mean you're just getting weird answers, and every time you run the application, the answer is different. And sometimes it's the right answer, sometimes it's the wrong answer. You can suspect, maybe I've got a synchronization problem. Maybe I've got one of these issues. There's a CUDA environment. There's an environment variable you can launch set, which is called CUDA launch blocking. And if you set this environment variable, the CUDA runtime API, whenever you launch a kernel, it won't just return control back to the calling process. It will actually wait until the kernel has finished executing before returning control. So this is generally very inefficient, and this is not how you want to write your application, but it's a very good debugging tool. So then if you run with this option set and you find that magically all of your problems go away, you know that you have a synchronization problem. And once you've determined that you have a synchronization problem, you have to start introducing synchronization into your application. And we're going to learn more about more advanced ways of doing synchronization later on. But the CUDA toolkit gives us a very blunt instrument for synchronization, which is a function call called CUDA device synchronize. So this is the call here. If you call CUDA device synchronize, that basically says, don't return from this function call until all work that's currently on the GPU has finished. So if you're running multiple different kernels on the GPU and you're overlapping all of your work, if you start calling this, you can start to reduce your parallel efficiency a lot. This isn't something you want to have actually sprinkled all over your code if you've got proper production code that you want to go fast. But it's a very good debugging tool, and it's also a very good tool to use in a limited way inside your application. So, given what we have just learned, now we can go back and first of all check whether we have a memory synchronization problem, and if we have, which I think it's pretty clear we have, we can run the CUDA device synchronize. We can insert this. You'll have to find the right location to insert this, and then have a look at whether that gets us the right answer. So, time for an exercise. And I'm going to no. Okay, let's get back onto some slides. So we're going to see, and I still believe that if you want to get the best performance on the GPU, you want to explicitly allocate memory on the GPU, because the best results are always even when you're putting an application, the best results are typically when you can figure out which data is going to be used on the GPU and then allocate memory for it on the GPU and copy it there and keep it there. And because the slowest point in your entire application or in your entire system is that transfer from host to GPU memory. So we're going to look at how to now actually just allocate memory that is just specifically reserved for the device, for the GPU, so that when you say, give me 100 megabytes on the GPU, you're going to get 100 megabytes on the GPU. Now this can be a bit more, there's more work involved here, because not only do you allocate memory on the host and on the GPU, but then you have to manually copy information from one to the other. But this has So it's maybe not the easiest way to start programming, but once you understand your application and you understand the data flow in your application, this is the best way to get optimized results as a general rule of thumb, or it's potentially you're going to get the best results because you can then hand tune exactly what data gets transferred when. But it is extra effort. So allocating device memory, we have a function called CUDA malloc. It works just like CUDA malloc managed or managed malloc. Size in bytes and a pointer to a pointer, where the pointer is what you're going to want to use for pointing to memory on the device, and CUDA free function. So we use the same CUDA free interface that we used for the managed memory. So here's exactly the same example we had before, and it looks exactly the same, except now we have CUDA malloc instead of CUDA malloc managed. So, yep, nothing new under the sun there. But we have an extra wrinkle in that now that we've allocated this memory on the GPU, we've got to populate it with data. So, and usually what we'll do is we'll have some data that we've created, we've allocated and initialized to some set values on the host, and then we want to copy it over. So we have to use CUDA memcopy. So CUDA memcopy is a function. It's very similar to memcopy, which is a function in the C standard library for copying blocks of memory from one spot to another. And CUDA memcopy, to copy a chunk of memory, we pass in a destination pointer. That is a pointer to the memory location where you want to copy data into, a source pointer, which is where you want to copy data from, a size, an integer value of size, where size will be the number of bytes you want to copy, and then some information about what sort of memcopy kind you want to have. Because when we're copying memory with a GPU, there's different copies we can make. We can copy from host to device, we can copy from device to host, or we can copy from one bit of memory on the device to another bit of memory on the device. And we can also do a memcopy host to host. I've never seen that used in anger, but these first three are useful. These are the types of memory copies that we're going to be wanting to do. Now this is a blocking copy because unlike a kernel launch, when you call CUDA memcopy, it actually blocks and waits until that copy has been performed before returning control to you. And later on, in a later part of the course, we're going to learn about the asynchronous version of this function. But for now, we're going to use CUDA memcopy. So let's say we're going to copy 100 doubles to the device and then back to the host. So we're going to create the values take some values that are stored in memory on the host, copy them to the device, and then copy them back. We first of all figure out the size of our buffer, which is again 100 times size of double. We've got 2 pointers. We've got a pointer to some memory on the device, which we just CUDA malloc, and then we also have a pointer VH to some memory on the host, which we allocate using malloc. And then we do a CUDA memcopy from, because this is the destination, this is the source. So from host to device of size, and then this flag, this memcopy kind, saying copy from host to device, and then we just do the same back. So you can imagine where after we allocate this memory, we might initialize it to some values, then copy it over to the GPU, and then do a bunch of work on that, and at some point do a bunch of work in here, and then copy the result back out, because we need to write it to disk or plot it or something like that. So one thing I haven't talked about yet, or in much detail, is that errors happen. So all of the API functions, they return error codes that you can use to test, was this call successful, or were there any errors? And if there was an error, what type of error was there? And you do want to check these. And you can check for whether the call you just made was successful. And you can also check if there was an error in an earlier call that you made. Because, as I said before, we make these asynchronous calls where you make a call to launch some work on the GPU, then you go off and do something else. when you make that call to launch, there might be an error. There might be a memory problem in your kernel that you launch, but you don't know about it when you launch it. You're only going to find out about that later on. So the API lets you actually ask, have there been any errors in any of the codes, in any of the kernels that have been launched before? So the error type is this enumerated type called CUDA error T. So for example, if we wanted to check CUDA malloc to see if there were any errors, we would go CUDA error T status equals CUDA malloc, or because we're using C++11, auto status equals CUDA malloc, and then we can test it. And there's two possible values that this can have. It can have CUDA success, which is the generic everything worked, we're all good. And then there's a CUDA error memory allocation. If you get that back, that means there was some problem allocating the memory. It's not terribly descriptive. It doesn't tell you whether it's because you asked for too big an amount of memory or because you ran out of memory. But these are your options. And then but this is just an error code. It's not so useful, or it's not so human readable to us. There's a function called CUDA get error string. So you can pass this status value that you get back in here, and it will then return a pointer to a string that contains an error message that a human being can read, so that when you print on the screen that there was an error, you've actually got a human readable error. Because this CUDA error T is just an integer underneath. So no one likes getting error messages like, oh, you had error number 63. That tends to annoy users. Okay, so we had our example of copying to the device and copying back again. This is just allocating some memory and copying to the device. This is what it looks like with error checking. Same as before, except now we've got this status here, a CUDA error T, and when we do the CUDA malloc, we get the status and then we check the status. And if there was a problem, if status was not equal to CUDA success, we print an error. And we do the same thing for the CUDA memcopy. It's really important that you test this, because if you don't test this, your program will crash somewhere later on, potentially much later on, and then you'll say, oh, my program's crashing here, but you'll have no idea that it was actually because you missed an error that happened back here. So you've got to do this checking. However, it's a pain. I mean, this code here wasn't too pretty, but this is really ugly. It gets very tedious writing this code, and very tedious actually writing it, and then the next person has to come along and understand it. So with that in mind, we're now going to do the next set of exercises, and we'll learn about how to make that a little bit neater by actually doing these exercises. So if we want to go to the exercise, to the API path again, it shouldn't be exercises/API, it should just be API/util.hpp. So in this util.hpp, the first thing to do is to find a function called CUDA check status and just tell me what that does. And then have a look. There's some wrappers for malloc host and malloc device, and just based on what we saw before, just figure out what they do. And if you can, try to come up with at least one benefit of using this sort of wrapper instead of just using a naked CUDA malloc and a free. And then, after you've done that, there's a test called explicit. So it has been programmed and it's ready to go, but if you run it, you're going to get errors. And to make it not get errors, you basically have to do step number 3 here. And when you've done step number 3 successfully, it will work. Because it's the same example we had before with the managed memory, except now we are explicitly allocating device memory and host memory and explicitly making the copies. And we haven't implemented these host to device and device to host copies. So when you run the application, it says make the copy, but no copy gets made. So when everything has been configured properly, the test should pass. So